Hello my friends, let's have a look at some nice exam questions from 2023 November and the possible extension for IA idea of polygon constructability. Without further ado, let's get started. Okay, so since the era of Euclidean geometry, the mathematics blossom in geometry, right? And the main concern from the Euclid is to talk about the constructability of a polygons. And very typical shape of a construction of a polygon is a triangle, right? And then you actually get to learn this in grade 6 or 7, right? And then constructability of a polygon relies on the use of just a ruler and a circle. Just a ruler and a circle is used typically for what is it? The constructability. That's representing the line equation. That's representing by the circle equation, right? So, and then the typical thing about the construction of the triangle was to just draw a line like that, and then from an arbitrary point, which I'm going to consider this as a the center of a circle, we draw some sector here. And then another point here, I will consider this as what as well, a circle of a center, and then we draw another radius here, right, another sector, and then the intersection point here, we will construct a triangle. That was the construction of a triangle in this case, right? And then a possible question that extends to a hard problem where you could struggle a lot is the constructability, for example, of a 7-gon, right? If you look at the heptagon, we know all the angles and etc., but we don't know how to prove it, whether it's possible to construct or not. But if you remember from your grade 6 or 7 study, it is not possible to construct the 7-gon polynomial just using the ruler or compass. Okay, so quite fancy, isn't it? But if I actually extend to more fancier number of the size to call it polygon is a 17-gon. And if you actually have a look at the 17-gon, it looks very identical to circle, right? Almost. And obviously we can talk about the internal angles and etc. And here, in fact, is it possible to construct the the 17-gon? And who draws the boundary? Who draws the line between the constructible or not constructible? And how can we actually prove it using the geometry or the algebra is going to be the main theme of this video. Okay. And in fact, if you quickly visualize this the polygon here. So this is a heptagon, but it's not possible. Right, and then if you actually look at the visualization of a 17-gon, which I prepared for you a very nice video at the end of the section, you will get to see how Gauss did it when he was around 20s in his dissertation to become a superstar for mathematics. We're going to have a look at those constructability using the complex number. Okay, so but in order to solve those problems analytically, what you actually have to gain understanding is previous exam questions. Now I will show you three very identical, similar exam questions from the past, and they're actually leading to you to convince you why those interesting questions come up for the exam, because they have the historical significance in mathematics. And if you look at the May 2011, what you had to do was to compare all applications of the complex number using the De Moivre's theorem or the binomial expansion, comparison between the real and imaginary part. You can derive many formula for the trigonometry, and somewhat you can actually find the exact value of cosine pi over 10. Okay, that's cosine 18 degree, and it's quite fancy method, right? And actually this sort of exam questions that compare with the DMT binomial and somewhat derive the quadratic form has been quite popular since. So if I show you another exam question from the May 2015, it's got the the expansion of the cis, the modulus argument form with the power over 5, and using the DMT you actually have to derive this form. And then what you have to do is to also derive the exact value of a sine 72 degree, which is a sine 2 pi over 5, using this quadratic form, right? So the quadratic relies on the complex number relies on this solution from the quadratic, and we wonder what the geometric significance it has as a solution. Okay, so let's have a look at the next question. So now, yes, in November 2023, exam question number 12 also has got something similar, right? The comparison of the real part, imaginary part. In fact, in this one, it's going to be the just imaginary part because we're just dealing with the sine, isn't it? And now, instead of a sine 2 pi over 5, they asked me to find the sine pi over 5 and 3 pi over 5. So let's quickly see what we can do with this, okay? And then another problem that you also have to remember to take the taste of proving the constructability of a polygon using the complex number is an exam question from May 2016. And here you had to somewhat work with this cis 2 power 7 and use it as a roots of unity of z to the power 7 equal to 1. And somewhat, the exam question asked me to find a quadratic, all right, using the omega square and omega power over 4 as a root of a quadratic, and you have to deal with its conjugate as well. But that's quite interesting, isn't it? Because why those arbitrary choice of the omega to the power 1, 2, and 4 is an interesting case. In fact, this is going to be the main application of building up a quadratic that is going to have some meaning for the constructability of a 17-gon polynomial. So please remember this problem. We're going to get back to it and solve it together and then see how we can extend it to the idea of proving the constructability, okay? All right, so let's have a look at the 17-gon constructability. I'm not going to delve into too much details of it, but we will get some taste of it, okay? We'll get some taste of those problems by accepting some lemma or theorems for free. Of course, if you want to study more rigorously, you know mathematics is all about the proof, so you also have to learn those proof and definition, but that will require you to have some knowledge of a tertiary level of education. This is a typical topics that's discussed usually in complex analysis, and you get to learn this in year 3 or 4 in college. So it's not a light weight. However, we could appreciate this topic using those exam questions and get some taste of it as an appetizer. So let's have a look. Okay. So let's have a look at the November 2003 question number 12. It was something to do with the quadratic equations using this complex number, right? So let's take a look. So yes, every time, right, you want to go from lower to higher power, you get to, using the complex number of the trigonometric identity, you get to use the DMT and binomial expansion and compare their parts. What do we mean by that? Okay, first of all, they asked me to expand it, right? So now it's got the degree 5 here. So using the binomial expansion, right, just to quickly remind you, it's a plus b to the power of 5 will be, what is it, sigma k is equal to 0 to 5, 5 choose k, a to the power of 5 minus k times b to the power of k, right? That's a typical expansion, isn't it? And then we can do the same thing here. If I put into the cis of that and using the binomial expansion, we got this beautiful expansion. But of course, complex number is all about comparing with the real and imaginary part, isn't it? So after the expansion, what I just did for you is to group by the real and imaginary part, okay? So this is the real part and this is the imaginary part. Easy peasy, lemon squeezy. Okay, so what we're gonna do now is to expand it in a different way. So we just use the binomial expansion, but complex number, higher power, boom, but yeah, we always have to consider for the de Moivre's theorem as well. So now we're equating the imaginary part of the DMT of the cis theta to the power of 5 is gonna get you, what is it? Cosine 5 theta plus I sine 5 theta, right? So that is the real and imaginary part, isn't it? And now I'm comparing the imaginary part from the DMT and then the imaginary part from the binomial expansion. That is jolly good. And now what we can do is also, if you look into the desired form, is everything is in terms of sign. But we had the form previously, what is it? Sorry. We had the previous form mixed with the cosine and sine, but every time you see the even power, my friend, every time you see the even power of a trig identity, you can use the Pythagorean identity to convert. So what I'm suggesting here is that I got the, what is it, cosine to the power 4 can be reduced down into cosine square, where cosine square can be replaced by the Pythagorean identity, such as 1 minus sine squared. Oh, sorry, I meant to write the theta here, isn't it? Okay, please, sorry about that. Okay, so but please bear in mind that we are using the argument as a theta. So that is great. So now it will lead up to the following form. If you do the expansion and then do some simplification, you're gonna get to that form. So please bear that in mind. If you want to derive the linear form, but the multiple of the angle of a sine, and then you want to derive something into polynomial form, you're comparing some real or imaginary part of a DMT with the binomial expansion, right? That's the technique that we do. Lower to higher power is, I call it, okay? So that is great. That's great. So now let's move on to the next part. So now what the question says is to find the solution of a sine pi over 5 or 3 pi over 5, okay, as an argument. Okay, so let's try that. So, they asked me to use that form, right? It's now in the quartic form, right? It's instead of a degree 5, but previously we had the degree 5. What I want you to realize here is that 1 over 5 is not an integer value, isn't it? So 1 over 5 pi is not going to give us a 0 because the sign is a 0 only for the integer pi input, right? So then I know, since it's not 0, what we can do is, from the previous form, if you let the theta to be pi over 5, boom, it will be non-zero, so I can actually divide both sides, right? So that's great. So I just divided both sides by the sign pi over 5, which is non-zero value, hence we got a quartic, right? So, but this is a quite friendly quartic, isn't it? Because now I'm using the substitution, I can make it into the quadratic form. So let's take a look. So now I got this quadratic form, right? So if I let the sine squared theta equal to t, where theta was, let's suppose it's a pi over 5, then I got this quartic polynomial, quartic polynomial converted into the quadratic form. I love it, right? That is great. And now, this is not factorizable, so we can use the quadratic formula, reduce up to this part here, right? And where the t was sine squared pi over 5, right? So now let's have a look. So now I got that part, but now because I got a perfect square, you can take the plus minus square root both sides, then I got the sine value to be the following. But so he's a function, he passes a vertical line test, so for the single input I must have a unique solution, but right now I got plus minus, you have to verify which sign you want to do. Okay, that's great. So if I then try to decide here where sine, I have a pi over 5, and that is an acute angle, isn't it? So because it's an acute angle, the outside has to be positive, right? So that is great. So since it's if you divide the 180 by 5, that's 36 degrees. So this is a 36 degree first quadrant. It makes all the trig ratio to be positive. So I gotta have a positive there. Okay, that's great. And therefore the outside is easily positive. What about the inside, right? What about this? So there are many ways to prove it. But one of the things that I like is to use the function. Every time you want to verify something about the domain and range, what I strongly encourage you to do is to sketch. Okay, so let's try to sketch the function. So the sine function is in fact always increasing from 0 to pi over 2. It is an increasing function in that restricted domain, right? And then pi over 5, right, will be strictly less than pi over 4. So because of the increasing function property, he must be less than or equal to sine pi over 4, which we know is a special angle. Hence the value is a square root of 2 over 2, right? So that's great. So in order to attain that value, the inside must be negative. If it's a positive, it's going to be bigger than square root of 2 over 2, which is the contradiction to the premise that the sine function is increasing. Okay, so that's what we can verify. It's going to be 5 minus root 5 over 5. Very good, very good. And then you can do the same thing for the 3 pi over 5, right? If you look at it, right, it's in the which quadrant is it? Yeah, you're absolutely right. It's in the second quadrant, isn't it? So for the second quadrant, I know the outside has to be positive. And if you think about this angle, it's very, very close to 90 degrees, isn't it? So it's slightly off here, but it's very close to 1, you see? So then, to make it very close to 1, I would choose actually the positive sign there. So now we got the sign, the exact value for the pi over 5 and 3 pi over 5 for the sign, right? That is great. So that's great. So then you can do the product here. I believe it will be just the difference of a square, isn't it? So if you use the previous result here, and if you multiply that inside, it's going to induce the difference of a square, then no problem. And if you do the algebra, then you get to the result. So that was the question from the November 2023. But I want you to realize this type of question has appeared many times. I showed you, wasn't it? It was I believe it was May 2011, May 2016, and now November 2023. Okay, but there's a reason. Every time you see this interesting exam question, some people use it to solve it for their entertainment, or some people actually extend their idea for the internal assessment as well. And this topic has been actually quite a popular topic of the IEA discussion because it actually links to something called constructability, right? It actually uses it for the constructability of a polygon. In fact, now I'm realizing I can actually find the exact solution of a 3 pi over 5 with either sine or cosine. And then if you pay attention to the denominator, this actually algebraically could tell you that it is possible to construct the polygon of side 5. The pentagon is constructible using just a ruler or circle. Who proved it? Gauss did. But we're not going to look into why the quadratic solution actually implies like the constructability, because it actually requires a lot of knowledge in the complex analysis, for which you're going to be doing in the 3rd or 4th year of college. But today we're going to just accept that as a truth. If I can find the quadratic solution in real number, oh yeah, don't forget, it has to be a real number. If I find the exact solution of those values, sine or cosine 2 pi over n, as an exact value using a quadratic equation, then yes, that n-gon polynomial would be, n-gon polygon would be constructible, right? So using the ruler and compass is our premise, okay? Okay, that's very interesting. So let's have a look at the sine 7x. For example, we said in the beginning of the in the introduction, Euclid couldn't prove the constructability of a heptagon because it's not possible, right? And if you for example, then what I just said was if you could derive, for example, sine 2 pi over 7 or cosine 2 pi over 7, I want to see if I can find the exact value of this using the quadratic form of some sort of extension of a complex number using the DMT and the binomial expansion. We can attempt. If you could find it, then you can prove it, right? That means you can construct it. Okay, so we can apply the method that we just did, right? We just expanded this by the DMT, and then we can extend it using the binomial expansion as well. So then if you want to compare which part, whatever, the real part, the imaginary part, it doesn't matter. But since we used the previous one with the sine, let's stick with the sine as well. Let's have a look at the representation of a sine 7x using the polynomial form derived from the binomial expansion. You know what? I did the job for you, right? You can obviously extend for k being odd, 1 to 7. It has to be odd number, of course. And I got this part for you. Of course, it's going to mix with the even power of a cosine. And I have already conducted the Pythagorean identity for you as well. So this is as simplified as it gets just in terms of sine, right? It's a very, very concise value here. And then we wonder if we can find the exact value of sine 2 pi over 7, letting the x to be, what is it in this case, 2 pi over 7, right? So if you have done that here, what you realize that, if you put the 2 pi over 7 here, 7 times 2 pi over 7 becomes 2 pi. Sine 2 pi is indeed 0. So then you can have a polynomial here using the substitution. Then sine 2 pi over 7 wouldn't be 0 because the integer angle, input is not an integer multiple of pi, so you can actually divide, right? So that is correct. So that this will be reduced down to degree 6 polynomial, isn't it? So yeah, we got that. Since this is non-zero, what we can do is to divide both sides. You have to plug in the 2 pi over 7, then I got the degree 7 polynomial, but what I can do is to reduce to that degree 6. But here's the thing, the premise of the lemma that we accepted for truth, as a truth without proof, is that I want to somewhat make this into quadratic form. Remember, from the previous example, we made it the quartic into the quadratic, which was pretty easy to see in that example because it was a constant quadratic and quartic. But if I look at here, I got the quadratic and degree 4. Is it meant to be degree 4? Sorry about that. I think, yeah, 2, 4, 6, right? It's got all that. Even if I, for example, try to make the t squared as a sort of another variable, it would not give me a beautiful quadratic form, right? It's going to actually give me a cubic form, and it's actually quite hard to solve, right? Because we don't learn the cubic formula, right? And what we can try here is to, have I solved this or not? Okay. So for this one, therefore, we can try to find the exact solution using the quadratic formula, but I just, let me remind you that it's not possible, right? So from that understanding, what we can say here is that it was possible to find the exact value of a sine 2 pi over 5 using the quadratic, hence it is possible to construct a pentagon. However, I cannot find the sine 2 pi over 7 using the quadratic. It is not constructible with the heptagon using the ruler and compass. But the method that we just used, comparing with the DMT and the binomial expansion, wasn't that neat because we saw a huge coefficient and a complicated polynomial such as a cubic, even if we substitute it. So we're going to take a different direction from different exam question in IB. You see, all those great exam questions has a reason because it's got insight from a history of mathematics. It's got this brilliant significance in the complex analysis, and we're gonna take some joy in it. Okay, so let's have a look. So now, of course, we want to have a look at the sine 2 pi over 17, but of course, expanding with the 17 power will give you degree 17 power. It will be very complicated to expand, right? So let's hold on to it. But what we can do here is, again, we're going to use the formula here or compare with the DMT and the binomial expansion. I've done it for you. You don't have to do it because it's just too much work, but it's a very, very tedious work, so let me quickly do it for you. But before doing that, let me take another approach of, deriving those angular formula of trigonometry, again, based on exam question. In May 2004, question number 5, it's got something called the Chebyshev polynomial. What is it? Let's take a look. So from 2024, you had to use one of those things to prove induction that this type of a function here, which didn't have a name, but let me remind you, this type of form appears quite a lot. It appeared on paper 1 in the back then, on the old papers, as well as a paper 3, using with the Maclaurin series, and it's got some significance in it. So let me quickly show you. If you want to derive some angular formula, what you can do is to make it into the polynomial form. And in the exam question of 2024, what you had to prove was that the t and x is always a polynomial degree n, right? So this is a very lovely problem, and I strongly suggest you to attempt this one as well. Well, let's take a look at it. But I want you to realize the first part here is to prove, what is it? Product to sum formula. This is a product to sum formula, all right? And then what you have to do here is to use the compound angle of a cosine, and then you realize if you do the compound angle, and in this time if you add them together, only the sine product of sines will be will vanish. So the cosine part gets double, so it becomes that, right? You can actually prove it using the compound angle. Easy peasy, lemon squeezy. Let's have a look at the next question. But for the second part here is induction. As you know, for the induction, you have to go for the basic step, and then that's the first step, and then you have to show the induction hypothesis implies the result proved, right? And here, what I want to show here is that you have to show the polynomial with the case for the n equal to 1 and 2 using some angular formula. If I put n equal to 1 here, then it's just the cosine of r cosine x, for which it is just a composition between the function and inverse function will just become the x, no problem, easy peasy lemon squeezy. But if I apply the cosine of 2 arc cosine x, as you can see, I cannot use the property of function inverse function right away, because if you multiply 2 on the function, it makes the dilation along the y-axis, so it does not hold the symmetry along the y equal to x. I don't like that, right? So what you have to do is to use some angular formula. In this case, I see the multiple of 2, it allows me to use a double angle formula. So if I use a double angle formula, then Bumbaya, what we can do here is 2 cosine square of r cosine x minus 1. Now I'm very happy because it's got multiple of 1, so you can composite right away. So, and some people actually get it confused with this composition. Let me quickly remind you, this is the same as cosine of arc cosine x perfect square. Okay, students often make mistake of just compositing once and leave out the cosine still, but that's not what we're doing. We're compositing first and then put the perfect square. So then using the inverse function property, this will become just the x. I'm squaring it, it becomes x squared. So I got the 2x squared minus 1. I'm very happy. Okay, that is great. So now you have to show also the following identity using the product to sum formula with the cosine a plus b plus cosine a minus b will become 2 times cosine a cosine b, right? So then if I use that formula right here, where n times r cosine x is going to be my a, and then the r cosine x is going to be my b, so it's a plus b, a minus b right away, right? So then if you use the identity, you can narrow it down to the 2x times t and x as desired from the identity that we proved from the product to sum formula. Okay, that is great. Now let's go for the induction. So for the basic step, what we had to do was to show n equal to 1. And if you put n equal to 1, cosine of r cosine x was simply just x. So I'm very happy with that, right? Okay, so now let's go for the induction hypothesis implies the result of proof. So let's dig in. So for the induction hypothesis, I'm letting the pk to be true. When n is equal to k, I'm letting the tk to be the degree k polynomial. You don't have to prove that because you're assuming that to be true. But what you need to do for the induction is whether the next domino is going to fall. So what we're going to do here is, okay, I want to see if the tk plus 1 is going to be a degree k plus 1 polynomial or not. I don't know that. For that, you have to prove it. All right, so then we can come up with the tk plus 1x as such. But then using the identity that we derived from the product to sum formula, you can actually reduce down into that form. Okay, and now that's very lovely, because I want you to realize for the induction, one way or the other, you must use the induction hypothesis. Now this tk plus 1x got reduced down to product of a linear and tk. and then the tk minus 1x, right? But if you look at the tkx by the induction hypothesis, that was a degree k polynomial. And then you are multiplying by the x, where you are increasing the degree by 1. Hence, this polynomial, by the multiplicative property of a polynomial, will now become the degree k plus 1 polynomial. That is lovely. So then I just proved that, okay, tk plus 1 also becomes k plus 1 polynomial, and it's easy peasy lemon squeezy. So we prove it by the induction for the all positive integer. And that is called, what is it? Chebyshev polynomial. Chebyshev polynomial is the composition between the cosine and n multiple of the arc cosine. Of course, you can do with the sine and n arc sine, doesn't matter. But the convention is to use the cosine. Okay, so that is great. So if you want that degree 17 using the Chebyshev polynomial, you can use that recursive form, isn't it? Because if I quickly show you back, this was the statement, isn't it? This was the statement. So what I'm saying here is that this is in fact a recursive relation. So if you wanted, for example, that polynomial of a degree 17, what you would have done here is plug the, 17. I will let the n plus 1, to be the 17. So n has to be 16, isn't it? So you put the 16 here, which is 15, and it's going to be 16. And to have those, you put it back recursively, you see? So it's like a Fibonacci sequence. So if I came up with the degree 1 and 2, right? I came up with the n equal to 1 and 2 as x and 2x squared minus 1, and mixing up with this, using this recursive relation, you can actually come up with the degrees 3. And because you have now degree 2 and 3, you can have degree 5, you see? So it's a recursive form, right? So what I would strongly suggest is you take a look into this, and it's actually a very, very lovely form to derive this multiple angular formula other than using the complex number and the DMT. So have I said it wrong? I said degree, if you have a degree 1 and 2, you can have degree 3. If you have a degree 2 and 3, you have degree 4. Sorry, it's not fully Fibonacci sequence, right? But it's the same kind because it's a recurrence relation, right? So if you wanted to have degree 17, you can start from 1 and then build up to all the way to degree 17, right? So this is what we did. So I've done it for you. It comes like that. Nasty polynomial, but I still managed, right? So that's great. So there's a different way to expand the angular multiple a formula for the sine and cosine. One was using the complex number and compare it with the binomial theorem, binomial expansion, or using the Chebyshev polynomial, which is another very nice exam question that has appeared quite often for the IB exam. And there's a reason for that, okay? All right, so now we got the sine 17x here. What was the whole promise now? Because we wanted to prove the constructability of 17-gon polynomial. When we said we just took the lemma for free, what was the lemma? If we could somehow build up a quadratic that has got the solution of a sine 2 power 17, okay? And using the quadratic equation or quadratic formula, and then find the exact solution in the real number, we conclude that it is possible to construct using the 17-gon polynomial, right? Just using the ruler and compass. That's the premise. And therefore, I need to somehow start with a polynomial. That's why we wanted to derive this angular formula. And what are we going to put here? Now we're going to put the x equal to, 2 power 17. Right, and then try to make this into the polynomial, and of course right now it is not the best form because I got the product of the cosine and sine. However, as we may have seen already, cosine even power can be converted into the multiple of sine, the power of a sine using the Pythagorean identity. Let's do that. So now all those even power, I have to plug it in. I can use the Pythagorean identity, and then we can simplify it down. Etc. becomes like that. And if I use the Pythagorean identity and then using the substitution, it came up like that, but I can extend it out for you. Let me expand for you. I already written it for you, so you don't have to actually attempt. But if you could, please do it. It's this type of algebra wrestling is very important for your own practice. Okay, so now I came up with this polynomial. Oh my God, OMG. Right? So it's actually quite hard to solve. And in fact, we are not just solving it. We also wanted to make it into the quadratic form, isn't it? Okay. So that's hard, you see. Why don't we ask ChatGPT to actually see if you can solve this, and if you could solve it, if you can actually put it into the quadratic form, right? So here, if we ask this language model such as a ChatGPT, and I ask him to solve it, somehow he's attempting to solve it, right, by using some constant multiple here, and then somehow he gets into the rabbit hole of a different, actual incorrect factorization. According to this, it looks like a very, very nice formula. Here I have a solution of only that one is possible to be the real, because everyone is a sum of a perfect square. It's not possible to find the solution in real number. So here x is gonna be just x squared is equal to half this implies that x is equal to plus minus square root of 2 over 2, which we know it is not correct, right? This is not possible for the sine 2 power 17 because that solution here is going to be sine power 4. So as you can see, we cannot rely too much on the ChatGPT using mathematics because he's not using the deductive thinking. He's just collecting the data collecting the information from the data, you see? So he's not solving it. So we cannot get much of a help from him yet, you see? Okay, so now how can we solve it? So can we gain more insight from another exam question from the complex number to see if I can build up a quadratic form of a sine or cosine 2 power 17. The sine and cosine doesn't really matter, right? It doesn't really matter. Okay, so now we're going to have a look at the May 16 problem. May 16 problem, the question number, I don't remember the question number, but it was at the end of the question number. So let's have a look. So in this case, what you had to do was to work with the cis 2 power 7, which is a root of unity from the 7 power complex number. So here what you had to do was to factorize using the polynomial and show that the sum of roots of unity actually becomes a 0. And you can prove this either using the geometric series or as you can see, the factorization. Look at this. Are we solving it? Let's have a look. Yeah, let's try to solve it here. So we just have to plug the cis 2 power 7 here. Using the DMT, this will become the cis 2 power, which becomes 1. So omega 7 minus 1 will be 1 minus 1, hence becoming 0. Easy peasy lemon squeezy. So if you expand this one out, if you do the distribution, you see there's going to be omega 7 minus 1, where omega was a root because it made it 0, didn't it? So we know it's going to be 0. However, as you can see, this cannot be 0. Why not? Because omega was defined to be, cis 2 pi over 7, and that cannot be 1 because in order for it to be 1 for the cis form, it needs to have even pi, right? Where k is an integer. And 2 pi over 7 is certainly not an integer, so I cannot have that, right? So now that's lovely. So what we can do here is that the sum of roots of unity here is going to become a 0, right? That is a lovely, that is a great. And then, so now, So what they asked me to do is to find another roots in terms of omega, where omega was a cis 2 power 7. As you know, it's just going to be omega powers up to the n minus 1. In this case, up to 6, right? That is a correct. So what you have to remember from that identity is the sum of roots of unity is in fact 0. And you can easily see that from the Argand diagram, because if you draw the Argand diagram, indicate all the complex root, if you add, the complex number on the Argand diagram is simply just a vector, isn't it? And from the vector form, you can connect them and then realize it's actually getting to the 0. Okay, so that's actually really, really important practice. And then somehow, the question now all of a sudden asking me to build up a quadratic equation, right? It got unhinged really rather quickly. It didn't have any context of working with the quadratic, but somehow it's asking me to work with the quadratic. Okay, why not? And here they ask me, okay, so I want this complex to have a root of alpha and alpha conjugate as the following. And we don't know why they arbitrarily chose those conjugate, but I'm gonna just accept it for free. I'm gonna take this one, okay? Okay, that's great. And here, if I somewhat use, the alpha conjugate, then conjugate is distributive, so I took the conjugate. If you multiply the omega 7, which is 1, right? Omega was cis 2 power 7, and it become a unity if you put into the nth power. So that became such. So showing that complex number is conjugate is pretty trivial, no problem, okay? And then what you had to do was to find those coefficients with the sum and product of roots of unity. Okay, so then for the quadratic form, already that it's alpha plus alpha conjugate will be negative b over a. So here a is 1, so b will be negative of the sum of roots here. So then if you add all that, you saw 1 plus omega going all the way up to omega n minus 1 is a 0. So if you shift that one out, then you see that it's going to be just negative 1. I got the negative coefficient here, becoming 1, no problem, right? For C, you can do the product also, right? Because for the quadratic, for the constant part, what you typically do is to put it into the product. So I've done it for you. So if you expand, and then you see, other than 4, 5, 6, these ones are bigger than bigger than 6, so then we can reduce it down, right? Because the roots of unity are uniquely determined. Otherwise, other than that, it will be just simple rotation by 2 pi. So for example, omega 7 is simply just a 1. Omega 8 will be the product of omega 7 and omega 1, which becomes here 1, so it's actually the same as omega 1. So if you actually reduce it down, this becomes from omega power 1 to 6, which becomes negative 1. So negative 1 plus 3 will give you, 3 minus 1. So that's what we have here. Okay, easy peasy, lemon squeezy. So let's have a look at the next problem then. Then using part B and C, I came up with this quadratic equation, so for which you can now find the quadratic formula, you see? And take this one, take a look at this one. So now your z is this, and then we already assumed that the roots were alpha and, the roots are going to be, what is it, alpha and alpha conjugate, where alpha was, well, I'm not going to call it, let's call it conjugate. Alpha was, what is it? It was omega square, omega 4. And alpha conjugate were the rest, I believe, right? Whatever. And then, it was the rest. But if I look at this alpha as omega plus omega square plus omega 4, it must be a unique solution, right? But now I got the plus minus. And how we can determine the imaginary part will be positive and negative is, again, to use the vector. So I got the real axis, imaginary axis for the Eigen diagram. And then omega 1 is just going up by 2 power 7, right? Omega square will be just slightly off from the power 2. Or omega 4 will be 8 pi over 7, so it's just slightly here, isn't it? So we're going to add those vectors. If you add those vectors, as you know, the resultant vector is going to be around here between these two. And if you add these two, the resultant vector is going to be around here in the second quadrant, where you know that the imaginary part here is going to be negative, isn't it? So, sorry, my bad. Imaginary part is a positive because it's going up. The real part is negative, which we can see, right? But then we had to determine with the imaginary part to be plus minus for the alpha. If you add, you can see it's in the second quadrant, so it must be positive. That's how you can determine whether it's a positive or negative, right? You cannot just say, oh, I feel like. You have to show. But other than that, what I also want to show is this, okay? What I also want to show is this. Why do we have randomly this quadratic, right? Think about this. Think about this. What we have here, my friend, was the alpha square, and then alpha 4, right? And his solution here is, negative 1 plus I root 7 over 2, okay? And where what was it? Oh, my bad, it wasn't alpha. The alpha is omega, sorry. Alpha is omega, okay? Where omega was what? Cis 2 pi over 7, okay? And that's great. That's interesting. And what you realize is that if you take the real part of alpha, that is going to be the real part of this omega square, omega 4, where you can use the DMT to expand. So it's going to give you, what is it? Pretty much the cosine 2 pi over 7, cosine 4 pi over 7, cosine 8 pi over 7, okay? But look at this. It's somewhat the sum of this value actually led into the complex number. So one of them must be actually a complex number, isn't it? At least, you see? But if a number is a complex number, then the other one also has to be complex number because it's a conjugate, isn't it? Or it may not be because they're actually not related. Sorry, only that and that is related because of using the, never mind, sorry, they're unique, they're uniquely different. We cannot use a reference angle or complementary angle to connect them. But what I'm just saying here is, so I know the solution of that is going to actually involve in the complex number because there's some actually, again, means the complex number here, you see, and that's actually a red flag for me to investigate the constructability of a 7-gun polynomial, because we know as we saw, oh sorry, not this one, but the cosine. So one of them is going to be a complex number, and that's not okay because what we said was if we want to talk about the constructability of n-gun polynomial, n-gun polygon, we wanted to investigate some sort of this in a quadratic form, and that solution using the quadratic formula had to be a real number, you see? But now it involves complex number, and that actually implies that it is not constructible using the ruler or compass, you see? But why? Why? Well, it would take some time. So for that, if you want to write this for your internal assessment or extended essay, I strongly encourage you to study the complex analysis and devour your knowledge of the high school math and the tertiary level of education to prove this beautiful lemma, right, or theorem, right? But now what we want to talk about here is that, okay, so if I can have from this exam question, I believe it was a 16 May, isn't it? I started with the sum of roots of unity of z to the power of 7 equal to 1, and I somewhat use its sum of roots to build up a quadratic, right, and then use it as a solution to verify the constructability. Well, I mean, the question didn't use it, but I'm just saying if you wanted to work with the 7-gun polynomial, that's how I would have done, right? Using the lemma that we got it for free from Gauss. Okay, And it was quite interesting because the question somewhat asked me to build up a quadratic of omega squared omega 4. But why? We haven't really discussed why. But it's interesting, okay? And I want to use that idea for 17-gon polynomial. Previously, we attempted two different methods. We used the DMT and then the binomial expansion. And we also used, the Chebyshev polynomial with the angular formula. We came up with degree 16 polynomial, but it was impossible to solve it. Even ChatGPT couldn't factorize it for us, right? So we're going to take a different approach. Now the third attempt from another exam question from the 16, where I'm going to now start with the roots of unity of a 17 and use some linear combination of those roots to build up a quadratic and see what I can get, okay? Okay, let's have a look. So checking with the 17-gon constructability, what we now agree to do without actually having fully proven, but we're going to just take a taste of it. So let's just accept that if we can find the exact solution of cosine 2 power 17 using the quadratics, it's going to be enough, okay? Sure. Let's take a look at this. Let's have a look at the approach. So now what we're going to do is the roots of unity. If I have a z17 equal to 1, as you know, the roots of unity is going to be cis 2k pi over n, where k is going from 0 to n minus 1, so I can have this root from 0 to 16 is my roots of unity, right? So then I'm going to, if this is omega, it's a cis 2 power 17, the rest will be 1 omega squared going all the way up to omega 16, so we got exactly 17 of that. And then what we also proved from the exam question is that sum of roots of unity has to be 0. Easy peasy, lemon squeezy, okay? So now we are going to now create 3 quadratics. I'm not going to come up with just 1, 2, but 3 quadratics using this linear combination of sum of roots of unity. Okay, let's have a look what I mean by that. Okay, let's take a look. So now quadratic number 1, you know what I'm going to do? I'm going to borrow the idea from the M16 problem where he came up with a quadratic of omega squared, omega 4. But now I had the 17 roots, excluding the 1. I got 16 roots, and from then I'm going to take 8 of them, and 8 of them will become like the one we had from the M16 problem. I'm going to have omega squared, but not only that, omega 4, and then omega 8. Okay, let's have a look. And then I'm going to take their inverse as the conjugate as another pair, so that I got 8 roots here. Okay, it's great. And you know what? I am not going to call the next one as a conjugate, but I'm going to call it as an alpha. Okay, let me quickly show you. I'm going to call the if when we had that, okay, another alpha conjugate were these 3, 5, 6, where you realize those are the missing roots, isn't it? These are the missing roots. Check this out. These were the missing roots, isn't it? They are 6, 5, 3. 1 to 4, where these were the solution of the degree 7, and then we know it consists of 1 to omega 6. You see, so if I had a 1, 2, 4, and then 3, 5, 6 were missing other than 1, were the conjugate they called it somehow. So if I call, let's take a look. If I call this as an alpha, I'm gonna call my another root of the quadratic of the missing roots. So if I came up with 1, 2, 4, 8, I'm going to go with, let's say, 3, 5, 7, 6, 7 are the ones that I'm going to choose, okay? So let's have a look. So if I came up with that alpha, okay, well, if this inverse notation is a bit confusing, what you can just multiply is omega 17, which is 1, then to make the things to be positive, and it's easier for me to see which ones are going to be missing, right? So if I do the missing roots here, it's going to be, omega 3, 5, 6, 7. And then I'm going to now add also with their conjugate also, but of course if the negative power is uncomfortable for you, what you can do here is to multiply by the omega 17 to make it positive. So I got that, right? So if I then do the, if I try to make a quadratic, right, then I know that the coefficient of, x here, coefficient of x will be sum of roots of unity, and then it's going to be product of roots of unity somewhat. And then we saw that if you add them through, 1 plus sum of roots of unity were 0, but so if you rearrange the 1 to the other side, it becomes just -1. So beautifully, this coefficient will be just -1. Double negative, it becomes a positive, easy peasy, lemon squeezy. So that's great. So that we already have alpha and alpha conjugate. If I do the algebra here, then these are just -1, so that's great. And you can actually multiply this as well. You know, we have 8 many terms. If you multiply, there will be 64 many terms. But if you actually perform the algebra, you realize that this is going to be simply just a -1. Okay, I've done it for you. But you can easily see why this will be -4. Okay, that is great. Now, using those beautiful numbers, I came up with a quadratic, right? So now we have the quadratic equation to be the following, where it's not factorizable, so I'm going to use a quadratic formula. But what I'm lucky with here is that it doesn't have the discriminant to be negative. It's a positive, so we got a real root. We got a root inserts. It's a rational number, right? So, and then also we have to verify when it's going to be positive, negative, and we can use the argument of adding the vector and see where my imaginary part will rely on. If it's in the first or second quadrant, it's gonna be positive. If it's in the third and fourth quadrant, it's gonna be negative imaginary part. But luckily now for the alpha, it was omega 1. Omega 2, omega 4, omega 8, and then all the rest will actually give you the imaginary part to be positive. So I'm going to use a positive root 17 for the solution of the alpha. Okay? All right. If you ask me why are you doing it, don't worry about it. If you actually delve into much deeper of this topic, you will see why those choices were made for the omega and then why we are doing this quadratic. At the end of this video, you will see why we need this alpha value. Okay. Now I'm going to move into the quadratic number 2. So now we started with 8 roots and 8 roots conjugate to build up a quadratic, right? But now I'm going to go half the size. Now I'm going to go with the 4 roots here and then the 4 roots there. Okay. How can we do that? Well, now I'm going to go with omega and omega 4. And then omega square, omega 8, those are the missing roots. But here's the thing. If you ask me, okay, why did you come up with this? Because for the first one, we kind of get it because we wanted to use a sum of roots of unity, just like the M16 problem, isn't it? But now, even if you add these two, it doesn't really fully give me the sum of roots of unity of a degree 17 complex number. However, if you actually add them through, beta plus beta conjugate, you see it's 1, 2, 4, 8, and then their inverse, their conjugate. You realize that's actually the definition of alpha. So beta plus beta conjugate can be just replaced by the alpha value that we got it from the previous quadratic using the quadratic formula. Okay, that's lovely. That's actually really, really brilliant. So now I got the beta plus beta conjugate. We have seen this one before. This was actually the alpha, isn't it? So that's great. So then we know the exact value of alpha using the quadratic formula. So now we got that, and then if we expand with the roots as we define here, and then we know that the beta conjugate will be simply alpha. I got it, right? And if you actually multiply the beta here, you realize it's gonna be just omega to omega 16. My bad. It just becomes -1. And actually, this construction of a polygon became very, very simple. Although the quadratic formula used will actually be more algebraically demanding because it's got some irrational number there, isn't it? But it's doable because it's the main algebra with the quadratic equation and square and the surds, and it's not bad, right? It's not even cubic root, it's a square root. It's okay. So I got this quadratic equation, which you can do first of all, checking with the solution being real or complex number. If I do the discriminant, boom-baya, I got the sum of a perfect square and a positive number, then it has to be positive, then I got the real roots. So now what we can do here is simply using the quadratic formula for which you get then the beta and beta conjugate like this. And of course, you have to verify whether my beta is going to be positive or not. And you can use the vector argument here to indicate the beta in this case will also should have the positive part. And then we have that, right? So that's great. So that is lovely. Okay, then we got a quadratic. So now I'm gonna move into the quadratic number 3. But think about it. Look, I'm gonna obviously show you which polynomial I'm gonna talk about, but I want you to also sit and think. Okay, I gave you the first quadratic made out of all the roots of unity for degree 17, you see? And then I excluded the 1, I got the omega power 1 square 4, 8 and their conjugate. Okay, so we had 8 of them, isn't it? But then I broke them down into half and I call it as a beta, right? And what do you think I'm gonna do for my next quadratic, which let's say now this quadratic has got the root of gamma, right? I got 4 roots. I'm gonna split this by 2. I got 2 roots here. Then it's gonna made out of omega 1 and omega 4. You see? So that its conjugate, if we add them through, it's going to become a beta, for which I know from the previous second quadratic, using the quadratic formula, I already have the value. So you can actually come up with a coefficient of x very, very easily. Okay, let's have a look. But what we are doing right now is why are we doing this? Why are we doing this fancy quadratic? Well, because we wanted to come up with a quadratic that has got the solution of cosine 2 pi over 17, isn't it? And as you know, cosine 2 pi over 17 can be expressed as a complex number and its conjugate. You see, the complex and conjugate is twice of the real part of z, isn't it? Okay, so I want to do that. And here, if I got the, omega cis 2 pi over 7, its conjugate is a negative 2 pi over 17, so then it becomes 2 times cosine 2 pi over 17, isn't it? Sorry, it becomes like that. Okay, so now I'm going to come up with a third quadratic, which got the root like that, where I'm going to call the alpha gamma prime to be the missing root omega 4 and omega negative 4, for which now if you add, it becomes simply beta. So look at this. A gamma, okay, is going to be what actually? Omega plus omega negative 1 is a twice of the real part of omega, where omega was a cis 2 pi over 17. So it becomes 2 times cosine 2 pi over 17. So very good, very good. So if I can come up with a quadratic with this gamma and gamma prime, and its solution will lead into the cosine 2 pi over 17, and if I can find the exact value of it, then boom, baya, according to the Gauss, back in the day when he was around 20s, proved this and then became a superstar, we now know that it is constructible for the 17-gon polynomial. Okay? Very good, very good. So what have we been doing? We defined the alpha, we made out of a bunch of the omega, and then they applied for the beta, and now what should we associate with the gamma? Very good. We're going to associate with beta, right? So then if I let the gamma to be the omega plus omega omega conjugate, then you see the, I'm going to call the omega prime to be the following, so that if you add, my friend, what does that become? Then it's going to be beta, for which we already know using the quadratic formula from the second quadratic, right? That is great, because then you already know the coefficient of the, the x, okay? So now if I let the quadratic to be the following, we got that. We already have the coefficient of x because it's equivalent to beta in fact, right? So easy peasy, lemon squeezy. So now let's extend. So blah, blah, blah. We already know this. So I'm going to plug that. No problem. So we already have got the coefficient of x using the sum. However, here, you know what? The product has been really beautiful, isn't it? The product of alpha and alpha conjugate, I remember it was a negative 4, you see? Product of beta, which gave you just negative 1. So no problem. So we think that the constant part will be very, very nice in this case as well. But in fact, it turns out to be the opposite. Here, the product of gamma and gamma prime leading to algebraic hell, you see? So, of course, this can be a very extensive study that you should take if you decide to do the IA and EE, or look it up. If you Google it, it actually explains why those choices of linear combination of beta, beta square, beta cubic had to be made to describe the product of the gamma and gamma conjugate, but it's rather lengthy, okay? So for your convenience, I've done it for you. So let me quickly show you. So if it's been very satisfactory for the alpha and alpha conjugate, it became just an integer value, right? No problem. But now it becomes really, really hard, right? So of course, things are not going to unfold as we expected. That's life, c'est la vie. But we can manage, all right? So now if you get the product here, it gives me such, but that is very difficult to describe just using beta. You need, again, beta, beta square, beta cubic, OMG. So we initially wanted to just use the bunch of sum of roots of unity, for which we did it for the alpha and beta. It doesn't work like that for gamma, okay? All right, so now if you do that, if you do the beta and beta square, and also have to use some multiple of the beta cubic, then it can be described as such, okay? I will leave it as an exercise why the constant part becomes like this, okay? That's actually very nice, because now you have a quadratic. Now you have a quadratic. So now, in this quadratic, using the beta and some sort of a beta and beta square and beta cubic, we got this beautiful quadratic for which you can use it, my friend, for the, quadratic formula. But before doing so, let's see if the real solution would exist using the discriminant. Well, if you look at the coefficient of bx, b squared is always positive. If you do the negative 4ac, if this is a negative, if you multiply by negative 4, it becomes a positive. So you are actually adding the positive numbers, which become positive. So the roots is going to be actually a real value. And now if you use the quadratic formula, you can finally find, so you can finally find the gamma, which is a root of this quadratic, where gamma was, omega and omega
conjugate, which becomes 2 cosine 2 pi over 17. Beautiful, beautiful equation, you see? So now let's have a look at the solution finally. That's the gamma here, and that, my friend, is a beautiful exact solution of cosine 2 pi over 17. And since now we got a beautiful quadratic equation that contains the exact solution of a cosine 2 pi over 17, you can say without sweat that it is constructible to build up the 17-gon polygon using just a ruler, linear line equation, and a compass, which is a circle equation. Okay, but of course, you have to know why. Why? How can we say that? It's a rabbit hole of a complex analysis for which you can take a look if you really want to learn this thoroughly. Okay, but I'm just letting you know this has been made because of the aesthetic of. I'm just going over this example because of the reason, the beautiful, insightful reason behind those exam questions and often the recurrence of those problems in the exam, because they want you to know what such delightful mathematics the ancestors have already done it for you, right? Mathematics is really the history of smart people, of their deductive knowledge, and those problems, those techniques, or the algebraic skills they have done, and then we are learning them through the history. Okay, good. So those are the algebraic proof of a constructability. What I've also prepared for you is an animation of actual construction of a 17-gon polygon using the compass and ruler. Okay, and I want you to enjoy this. Let's take a look. All right, thank you for watching. Spend some time for creating the animations. Please enjoy that, okay? But as you can see, more related problem with the polygon and construction with the complex number is evident in many exam questions. If you take a look at the May 2021, using on paper 3 is the geometric property of roots of unity. You see, we saw the geometric property of roots of unity for the extension to the complex number with the constructability. Again, it's visible in the paper 3, and there's a reason behind those questions' appearance because of the history of mathematics, right? So the examiners are great in terms of making these questions. It's not random, you see, it's got historical significance in mathematics, okay? But yeah, that's pretty much it for me today. Since as soon as I saw the November paper, I realized, oh yeah, this is great. There's a reason behind it, okay? And I don't want you to just solve the problem without fully understanding why those beautiful questions come up with, because it's actually quite a nice problem, isn't it? Because that question single alone contains binomial expansion, De Moivre's theorem, complex number, trigonometric equation, and function and identities. It's got everything. It's a topic 1, 2, 3, you see. But there's a reason behind it because of the beautiful, beautiful extension of the constructability, which was proven fully by Gauss in his 20s for his dissertation, which made him a superstar. Okay, so I want you to take a look at that, please, and enjoy the video. That's it from me today. See you around.